Hi and welcome to this webinar about how to set up a 3D CFD case in LS-DYNA. My name is Marcus Timgren and I'm working at DYNAmore Nordic, and if you have any questions please contact me at my email address that you can see here on the slide. Today we're going to talk about how to set up a CFD model in LS-DYNA. First we will address how to create the mesh, and then the different keywords that is needed for the model, then how to output the results and how to run and look at the results. So the eCFD solver has an automatic measure. So as a user you mesh the surface of your fluid volume, and then the solver will generate the fluid volume. So this is a cross section of the fluid volume, but of course it's possible to use a user-defined mesh if you want, as long as you use tetra elements in 3D and triangles in 2D. So this CFD model that we're going to set up today is flow over a plate. So you have one inlet here and an outlet here, and then the plate in the middle, and all the units are in SI units. So the measurements here are in meters, and the inlet is part 1 and the outlet part 2, and for the domain boundaries we're going to use a free slip condition, and from the ground and the plate a non-slip condition. And the fluid is set to air with a density of 998.2 kilos per cubic meter and a dynamic viscosity of 0.001005 Pascal seconds. When you use the automatic measure, you have to think about a few things. The first thing is that you're going to create your model and mesh it with surface elements, and then you have to create a part for each boundary condition that you're going to use. So for inlet, all those elements belong to part 1, and for outlet they belong to part 2, and for the domain boundaries they belong to part 3, and for the ground part 4, and for the plate part 5. After you have done that, check that you don't have any duplicated nodes and that all the boundaries are connected. And if you're using a different preprocessor than LS Prepost, output the mesh in a LS-DYNA format, since at the moment only Primer and LS Prepost supports the eCFD keywords. And to get a similar mesh to as in the picture, use a mesh size of 0.09 meters for part 1, 2 and 3, and for part 4 use a mesh size of 0.05 meters, and for last part 5, use a mesh size of 0.04 meters. And when you have output your mesh or finish with it, you have to convert it to the eCFD mesh format. And you have two options for this: either use a text editor and change the element shell and node to mesh surface element and mesh surface node respectively. And the second option is to use LS Prepost by opening your mesh file and then press mesh MS Mesh and then select by part and press the whole, so you get the whole model, and then enter starting PID to 1 and then press apply and accept. Then you can save the model as mesh_fluid.k. In this presentation I will use LS-Prepost to demonstrate how to set up this model. So the first thing to do is open LS-Prepost and then use the keyword include to include the previously mesh file. So find the mesh_fluid.k file and include it. And then save the model as main fluid.k, for example. And to load the mesh file and view it in the LS-Prepost, we have to close the program and open the main_fluid.k file again. Then we're going to add the eCFD section keyword. So use the keyword manager located on the model keyword to add new keywords. So eCFD section is needed for the part keywords, but it doesn't have a purpose, so just double click on it and press accept. The next keyword is eCFD mat, which defines the fluid properties. And in our case we're going to define the density to 998.2 and the dynamic viscosity to 0.001005. And then press accept. And then you can associate this with each part. So modify the eCFD part keyword in the keyword manager and check that you have the correct section ID and material ID. Then press accept and do the same for the other parts. Now we're going to associate these properties to the fluid volume. So use the keyword eCFD part vol, and here we're first going to select the previously created section ID and material ID. Then we're going to enter the parts that enclose the fluid volume. So in our case part 1 to 5. But in cases when you have more than 8 parts, it's possible to insert another row. So this keyword can have multiple rows here. So you're not limited to 8 parts. So when you press insert and accept, we're done with this keyword. And now over to the boundary conditions. Here is a list of the boundary conditions that are available in the R9 version. And for inlet and outlets, these 3 boundary conditions are used. The pressure and the velocity is the mostly common used, and eCFD boundary prescribed turbulence is only used for RANS turbulence models. And for walls, the following 3 boundary conditions are used: boundary non-slip, boundary ground, and boundary free slip. And the boundary free slip is also a symmetry condition. And when the heat equation is activated, the eCFD boundary prescribed temp is used and the eCFD boundary flux temp. And for FSI and conjugate heat transfers, the eCFD boundary conjugate heat and eCFD boundary FSI is used. And then we also have a boundary condition that creates a wave at a certain part, and a condition that prescribes a motion of a part. Now we're going to define the inlet condition, and we're going to use eCFD boundary prescribed well, and it requires a load curve, so we're going to start with the load curve by using define curve, and then we're going to use a ramp, so between 0 and 1 second the velocity will be ramped from 0 to 1, and then after that it will have a constant value of 1. So for the third point, enter a high value here and then keep the ordinate value as 1. And then press accept and press new ID and create a new load curve that is constantly 0 for the pressure condition. To define the velocity, locate the keyword eCFD boundary prescribed well and enter the part ID 1 and the degree of freedom 1 and use the load curve 1. And then enter a scale factor of 40, which means that our velocity will be 40 after the ramp has finished. So after 1 second. And then set the other degrees of freedom to 0 by using load curve 2. So press insert after each new degree of freedom and then press accept. For the pressure condition, we're going to use the eCFD boundary prescribed pressure and then select part ID 2, which is the outlet here, and then load curve 2 that it has a constant value of 0, and then press insert and accept. For the ground and the plate, we're going to use a non-slip condition, so locate the eCFD boundary non-slip and select the part 4 and 5 and then press accept. And for the domain boundaries, we're going for part number 3, we're going to use a boundary eCFD boundary free slip and select part number 3. To control the time step and the end time, eCFD control time is used. So set the end time to 1.5 seconds and keep the time step to 0, which means that an automatically calculated time step will be used by the solver based on the CFL criterion. And another good keyword that can be useful to use is eCFD control output. And the first parameter controls the output level, how much information that is printed to the message files, and the other next parameter outL controls in which format you will get the results, and the third parameter controls how often those results should be printed, and the fourth option activates an output of the fluid volume mesh in a format compatible with LS prepost. And to generate the fluid volume mesh, the keyword mesh volume has to be defined. And this keyword tells the solver where to create the fluid volume mesh. And in our case, we're going to use all the parts, so part 1, 2, 3, 4, and 5. And then press insert. And if you have more than 8 parts, define your first 8 parts and then continue with the rest and press insert. So this keyword supports more than one row. And the mesh in this example is quite coarse, and that is to save computational time, and for the same reason the boundary layer elements has been removed. But you can add them by using mesh BL, and you can check the presentation on how to set up a 2D CFD case in LS-DYNA if you want to know how to use that keyword. And the reason for the coarse mesh is that this example will be used in FSI simulation. To control the output level of the dt-plot files, database binary dt-plot is used. And locate it and open it and change the dt parameter to 0.05 to get 30 result states during this simulation. Then press accept and done. And for outputting eCFD data, you can use the database keywords, and the following three are useful for this case: eCFD database drag, eCFD database time step, and eCFD database flux. The drag keyword outputs the drag forces on a given body or part, and the eCFD database time step outputs a file with the solver's time steps and the CFL time steps. And eCFD database flux output the volume flow rate over a part. So in this case, use it for the inlet and outlet, part 1 and 2. To run the model, you have to use a double precision version of LS-DYNA, and I recommend you to use R9.0.1 or a higher LS-DYNA version. And for Windows, I recommend to use LS-Run to start your simulations. It is a really good program to start both MPP and SMP calculations. And it can be downloaded for free at our FTP site here. And on Linux, I recommend you to look in the keyword manual for more information on how to start the simulation, since it will look different for each setup. We're using a script to start our MPP simulations, and our command line look like this. But you could also use LS-Run on Linux if you want. And if you in LF prepost, if you click on file and then run LS-DYNA, then you will open LS-Run with the current file loaded, and then you can just press run the model. The model takes about 4 minutes on 4 cores, so it's quite a small model. Here is some modifications that you can test on the model. You can start with refining the mesh and see if the result will change, or if they still mesh dependent. And you can add the boundary layers with mesh_BL. Change the velocity and see how it will affect the results. You can change the turbulence model with CFD control turbulence. And the following turbulence models are available in R9. The variational multiscale approach, which is the default value, runs co-epsilon with two submodels, standard model and realizable model. Then large eddy simulation, LAS, and here we also have two submodels, Swarovski subgrid scale model and wall adapting local eddy viscosity whale model. And then we have the runs co-omega models. Here we have standard Wilcox 98 model and standard Wilcox 06 model, and the SST Mentor 2003. And then we have Rans Spalt and Marsh approach. To post-process a 3D case, we have to look inside the fluid volume, and that is possible by section planes. So open the D2plot file in LS Prepost, and then you will have a window looking like this. So we're going to start by hiding all the shell parts. So check them and then press MS Solid and set the transparency to 5. And now right click on MS Solid and select section and change the normal of the section to be in the Z direction, either here in the object properties or in the graphical window. Notice that you have to have the section plane activated to view the object properties and change the normal. And to plot a variable, change color by to, for example, fluid velocity, and then you can see how the fluid velocity develops over time. And here you also control all the Legion properties for that section plane. It is also possible to group similar objects. So for example, if we create two section planes, one in the Y direction and one in the Z direction, and then hold Control and click on both, and then right click on them and select Group. Now and click on the group. Now you can color these two section planes by fluid velocity, for example, and then change the fringe level to 20 and see what happens. And it should look something like this. So here we have 20 colors instead of 10, and two section planes but one legend, since we changed the properties of the group instead of each individual section plane. If you want to find where a certain parameter has a certain value, you can use isosurface. So uncheck all the other objects that you have created and right click on MS Solid and then select isosurface. And then in the object properties you can select the fluid velocity parameter and set the ISO threshold to 5. And you can also change the component here from magnitude to the velocity in X, Y or Z direction. And then in the display option you can also color the fluid, the ISO surface with a parameter, for example fluid pressure. And if you look in the object window, you will see that the ISO surface will have a star in front of it, which means that it needs to be updated. So right click on the ISO surface and select update to view the ISO surface. And here you can also control the mean and max values of the displayed fluid property. And if you want more information on post-processing, check this video out. And here I've colored the ISO surface with the pressure, and I have taken the ISO surface with the velocity magnitude of 5 meters per second. So this is how it could look like. Here you can see how the fluid velocity develops over time. And as you can see, it reaches a steady state when the velocity reaches its constant value. But I'm pretty sure that if you refine the mesh, you will see that you get a more unsteady flow around the plate. So that was all that I had for this tutorial. And thank you for listening.